Okay, so we're gonna continue the major themes of anatomy and physiology. We discussed in our previous illustration that we have four micromolecules that give us four micromolecules that give us four macromolecules. That's a good occasion to review. Who can mention for us the first micromolecule we talked about? Amino acids. So we have number one, amino acids, and they build up to give us what? Proteins. And what else do we have? Monosaccharides. Monosaccharides give us disaccharides. And many disaccharides give us polysaccharides, known as carbohydrates. Carbohydrates. Proteins are known as polypeptides also. Then we have another type. These are your nucleotides, and they give us nucleic acids. And lastly, we have the glycerol and free fatty acids. They come together, and all of that gives us what? Lipids, also known as fat. And remember, we don't only build up. The highway has two directions. There's an uptown trip and a downtown trip. So we build up to get the macromolecules. You need to know that. You need to know that the guys at the top are the macromolecules. Macromolecules. And the one at the bottom are known as micromolecules. Are we clear? So you need to have both. Up and down. The elevator needs to go up. Imagine the elevator just goes up. You need to go up and down. Subway. Uphill, downtown hill. So now, downtown hill. Uphill, downhill. I'm too tired. Nucleic acids, back to nucleotides. And lipids, back. So why are we doing that? Because when you go from micromolecules to macromolecules, you are storing. You are storing. So when you have a lot of glucose, you store it in the liver, it becomes glycogen. You have a lot of glucose, you store it in the muscle, it becomes glycogen. You have a lot of nucleic acids, you store it, you have a lot of nucleotides, you store it, you get nucleic acid. Now, this is known as, you have a lot of fats, you eat a steak, then that's going to be converted into lipids. So this is known as storage. You need to store, right? When you go out shopping, you bring the vegetables, you store them in the fridge. But when you're hungry, you take them out the fridge. You chop them up, you break them apart, you cook them. So your body needs to be able to store. So storage is known as anabolism. What is that? Anabolism. Anabolism. When you're storing, when you're going up, when you're building, you have the little tiny building blocks, you're storing them together in order to get a huge macromolecule. And that is known as anabolism. So when you're building up, for all of them, there's anabolism. There is proteins, anabolism. There is monosaccharide, carbohydrate, anabolism, nucleic acids, anabolism, and lipids and fats, anabolism. Yes?
But when you store it, it's the micro.
No, when you store it as big. But when you break it down, that's catabolism. When you go down, this is breaking. Breaking down, this is known as catabolism. That is, when you break down, it's called catabolism. So the two directions, anabolism, catabolism. Building up, anabolism. Breaking down, catabolism. Building up, anabolism. Breaking down, catabolism. Are we clear? Questions? So building up, anabolism. Breaking down, catabolism. Okay, guys. So those two things, anabolism and catabolism, they have a name. What's the name for both anabolism and catabolism? Metabolism. Excellent. So metabolism is the sum of both catabolism and anabolism. Anabolism is storage and catabolism is break down. Is that part clear? Okay. So anatomy is the study of the structure. We went over that. The structure, the function, and anatomy and physiology, they are complementary. They can be studied as standalone. There's a course that says just anatomy, a course that says just physiology, but actually they are interdependent and they are based on each other. You will never have a physiology unless you have the proper anatomy, and the proper physiology requires the proper anatomy. So they are not enemies, they are interdependent. So the surgeons need to be familiar with different versions of anatomies for anatomical variation. We talked about gross anatomy. Remember, gross anatomy is naked eye anatomy, meaning that it's the anatomy that we are able to see with our eye. We don't need microscope. Very good. Histology is microscopic anatomy. So that's the examination of the tissue with the microscope. Histopathology is the studying of the development, the mechanism of the, not again. Oh no. It's back. It's gonna go back again. Okay. Histopathology is a combination, is when you're studying the molecular mechanisms that lead to disease formation, how to propagate and make the disease formation. Cytology. Ology is the science of the knowledge of the learning of ology. Cytology is the study of structure and the function of the cell. That is when we study the cell plasma membrane and the cytoplasm and the cytosol and the different types of organelles and the nucleus and the DNA. So all of that is cytology. All of that is the cytology. Hooke's microscope. So Robert Hooke was the first to find out that the same way we have telescopes, back in the day, the telescope was used to look at stars in space. Now he thought the microscope can show us the space that we cannot see. So we have a universe that is beyond us, but there is another universe that we cannot see with our eyes. All of the different types of organelles. So he began, and that was the simple, most primitive compound microscope. Now, this guy here, Van Leeuwenhoek, was the one who was able to understand you can combine different lenses to magnify exponentially. So if you look at the microscope now, the microscope has multiple lenses. The microscope has a lens in which you put your eye. This one here, this is known as the ocular lens. Ocular because you put your eye on it. And then the ocular lens is going to bring you down to 3 different types of lenses. Each one has a different magnification. Then you have a stage, and on the stage, you have your slide. So there is an ocular lens that gives you an ocular magnification. Ocular lens give you an ocular magnification. And you have an objective lens that gives you an objective magnification. Clear? The law is total magnification, total magnification. The total magnification equals ocular magnification multiplied by objective magnification. Ocular magnification multiplied by objective magnification. Are we clear? So now the ocular magnification is always 10 times, 10x. The ocular magnification is 10 times 10x. The objective magnification is usually 10x, 40x, or 200x. Now, we all agreed that all the tissue slides do not look the same, don't have the same structure, don't have the same function. So in order for me to visualize a particular tissue slide, I'm going to need a different combination, right? So I'm going to multiply. So let's say now I looked at a tissue slide using the ocular lens and the 40x. What's my total magnification now? Exactly, because I multiplied by ocular magnification, 10, multiplied by my objective magnification, and that is 40. 10 times 40, that is 400. So now he gave us the idea that you can combine and you can put lenses and to increase the magnification. Now, these two guys came up with an excellent theory, and that is the cell theory. Because all of living organisms are made of cells. Because the cell is the basic unit of life. This thing here is not alive because it's not made of cells. So remember, it has metal, and metal is part of cell. You know, the cell has a lot of magnesium, it's a lot of iron, but that doesn't make it alive. The cell is alive. So everything living is made up of cells. The bacteria is alive because the bacteria has at least one cell. There's unicellular bacteria. These are the prokaryotes. The fungi, there are multicellular and unicellular eukaryotes. We are multicellular eukaryotes. There are different types of organisms, but you will never be alive except that you are made up of you're made up of a cell. The cell is the unit of life. So he came up with different types of tenets. Number one, we all discussed that the functions of your body are the sum and collection of the activities of the cells. So for example, your digestive system is able to digest because there are cells that work to digest. For example, your oral cavity is responsible for ingestion of food. That is its function. Your esophagus is responsible for the propulsion. Is propulsion and ingestion the same thing? Is that the same function? No. So that means the cell. If you take cells from your esophagus and cells from your oral cavity, are they going to look the same? No, because they have a different job. The stomach is responsible for compaction, crushing, grinding, churning of the food. That's different. That's digestion. It's different from ingestion, different from propulsion. Your intestine is responsible for absorption. Is absorption of food the same thing as digestion and ingestion and propulsion? Your large intestine is responsible, your rectal canal is responsible for the excretion of waste. Is excretion the same thing as ingestion and digestion? Obviously not. So those cells, they're all going to look different. But the combination of all the cells is what gives us the function of digestion. So all of the functions of the body can be traced back to the sum of the actions of all these different types of cells. Okay? So now, cells do not come except from pre-existing cells. Cells don't come out of nowhere. I am here because my parents are there. My parents are there because my grandparents are there. My grandparents are there because my great-grandparents are there, and so on. So people don't come out of nowhere. We come out from cells. You are alive, you have to have cells. You cannot be alive and you don't have a cell. What is inductive versus deductive reasoning? What is inductive versus deductive reasoning? Inductive, inductive versus deductive reasoning. Inductive versus deductive reasoning. What is that? Well, both of them are forms of reasoning. Both of them are forms of reasoning. We reason with them. Inductive reasoning and deductive reasoning. So what does that mean? Deductive reasoning means when you have a rationale that is based on a fact, or a pre-established premise. You have a pre-established premise or a fact, and you deduce from a fact or a pre-established premise. What does that mean? Let's say someone tells you all mammals have hair. You know, that's a fact. That's a fact. All mammals have hair. The bear has hair, and you know, the humans have hair. All mammals have hair. That's a fact. That's a pre-established premise. All mammals have hair. All mammals have hair. All mammals have hair. It's a pre-established fact, pre-established premise. Then your friend tells you, listen, the whale is a mammal. Then you say, then it must have hair. That's an example of deductive reasoning because you deduce from a pre-established fact. Did you go in the ocean and touch the whale and find out there's hair on the skin of the whale? You did not. You based on a pre-established fact and a pre-established premise. Someone tells you all mammals breastfeed milk to their babies. And you see the whale breastfeeds its baby, the humans. Then someone, the bear is a mammal. You say, well, absolutely the bear is able to breastfeed its baby because you build it on a pre-established premise. That's deductive reasoning. Inductive reasoning is different. Inductive reasoning is when you are not deducing, but it's when you're reasoning based on a diagnostic, or based on a investigation. So for example, I come into the clinic You take my blood pressure is high, then you say he must have been running to be on the appointment on time. So how did you know that my blood pressure was high? Because you took a diagnostic measurement, you measured. So there is an investigation, diagnostic investigation, measurement. Say, oh, I have pain in my flank. You do a sonogram, there's a stone in there. Say, oh, you have a kidney stone. How you don't have a kidney stone? Did you have a pre-established premise, or did you investigate with a sonogram? You investigated with a sonogram. You did a CT scan. You found out the lung has cancer, God forbid. You did an MRI. You found out there is a disc herniation and the vertebral column is crushing the nerve, causing sciatica pain. How did you know all of that? The magic, or did you actually do the MRI? So you looked into the diagnostic. That's inductive reasoning. So when they went in the ocean and they got the whale and they did a histological analysis and they found out there was hair, that one wasn't deductive. That one was inductive because they actually measured and did diagnostic intervention and they investigated and they took a look in the microscope. So that one was based on inductive reasoning. But after this, the fact was made. Then if you rely on the fact, then that's deductive reasoning. Are we clear? Clear. Deductive reasoning, inductive reasoning? Okay. All right. So now, when we move into, that's the hypothetical. All righty. So, inductive, deductive reasoning. Now we're going to move into, you always, the number one most important, essential requirement is the sense. So the sense leads to the observation. The sense leads to the observation. The observation leads into the hypothesis. The hypothesis leads into the experimental design. And the experimental design is going to give us the results. Then we're going to do a discussion. Then after the discussion, we're going to peer review. And lastly, after the peer review, we're going to have our conclusion. What does that mean? So, sense. You know, Isaac Newton, when Isaac Newton saw the apple fall, he saw it. He saw it. Did he hear it? Did he have a dream? He saw it. So if he didn't see it, will he have been able to observe that the apple fell down and there must be gravity that pulled it down? So always the sense leads to the observation. You're walking in the street, you saw an apartment on fire. So you call 911, you say that, please send the ambulance to so-and-so. How did you observe there was a fire? Because you saw the fire. You saw the fire, and then you were able to call. You saw the fire, and then you were able to call the. So you base your observation on a sense. You heard somebody screaming for help. There is a criminal in the house, so you call the police for them. You heard somebody want the ambulance, so you call the ambulance for them. So the observation is based on the sense. So scientists who come up with great observations and discovery, and they get Nobel Prize, they have excellent senses. They're not dull, dumb, insensitive people. The insensitive people, they don't observe. They are insensitive. They don't observe, so they don't care about other people, and they don't feel anything. They don't feel for themselves. They don't feel for other people. But if you're sensitive, you will have good observations. You have good hypothesis. You'll be very brilliant. So the observation is going to lead to the hypothesis. Now, the hypothesis is always an if-then comes in the format of if then. So I have a hypothesis that if the blood pressure is high, the breathing rate will also be high. Well, that's a hypothesis. If then. Why is it a hypothesis? Because I can test both. I can test the blood pressure and I can test the breathing rate. Now, let's say I come and say, if God is mad at you, your blood pressure will go up. I agree with that one too, but that's not scientific. Scientific, it has to be tested. Everything has to be testable. Many students think that because if something is not testable, like I can't say the ghost, or the demon, or the devil makes the people, have anxiety and depression. Well, that's not scientific. But just because if something is not scientific, it doesn't mean it's not true. It means that I cannot bring the devil and test the devil. He will run away. I cannot do that. So that's not scientific. But it doesn't mean there is no devil. It doesn't mean there is no God. But it's not scientific. So the science means everything. Oh, I'm gonna die here. Okay. So we have. Oh, the devil didn't like microphone. Okay, so we have to have a scientific design, meaning I can test everything. So if the blood pressure goes up, the levels of angiotensin converting enzyme will go down. I can test both in my blood. If cortisol goes up, the blood pressure goes up. I can measure cortisol, I can measure blood pressure. But I can't say if the demon possess you, your blood pressure will go up. Maybe it's true, but it's not scientific. That's not scientific. So don't think that because something, I only believe in science. Well, there is many things that are true, but they're not scientific. But remember, for us, everything has to be 100% scientific. Okay? Then you make an experimental design. Experimental design, you have to have, I want to test the effect of a certain medication on lowering down blood pressure. So I bring a room of 100 blood pressure patient and I split them in half. 50, I give them the actual medication to see if it's going to affect or not. And the other 50, I give them placebo, a medication, and they don't know what they're getting. So I can reference and see the effects of my medication. Now, back in the day, they used to tell the group, listen, you're getting the blood pressure medication. So they will say, so what if my blood pressure still doesn't go down? Does that mean something's wrong with me? So now their blood pressure is going up. And then some people, they say, well, since I'm taking the blood pressure medication, my blood pressure should go down. So that interferes now with the data. Some people, they realize that placebo works. Some people, they gave them medication for high blood pressure, and they realized that their blood pressure actually went down because they thought that way. They thought that, well, I'm getting the medication. Some people, they have like some holy lake they drink from. So, if you drink from this holy lake, your blood sugar is gonna go down, and it does. Some people, they gave them some placebo medication that doesn't really do anything. They develop side effects to it, and it's not even a medication. So it's all a psychosomatic thing. The psychological, psychological state of mind. So that's what we're talking about, psychosomatic effect. The group that I'm going to give the placebo to is called the control group. But the group that I'm testing is the experimental group. Are we clear? Okay. Something that you also need to know is the double blind versus single blind. So the single blind, they solve the problem by, now you don't know which group you're in. You're just going to be given a medication. You don't know if it's actually lowered the blood pressure or if it's actually a placebo. So you're natural now. The other problem was the scientists going around and saying, how's your blood pressure? Is it not? Doesn't make sense because you were given the placebo. So now the scientist is starting to interfere with the data. So now even the scientist doesn't know which group is getting what. So this is called double blind. Single blind is when the two groups don't know which one is control, which one is like you know you're a participant in the experiment, in the study, but you don't know if you're part of the experimental group or part of the control group. The double blind is you don't know, and the scientist running the experiment, he doesn't know either. So they don't tell him. Another group knows, but they don't see so it's all a team working together. So part of the team is everybody knows we're testing this drug effect on blood pressure. You don't know which part of the group you in. I don't know either who is getting what. But my friends, they know which group is getting what, but they don't see anybody. So now we make sure we divide everything fairly. So now the results are going to be as scientific as possible. Okay? But after the experiment is done, I'm going to find out. I'm going to go back and look and see, statistical testing. We use statistical tests to provide statements of probability that treatment was effective. Okay, when the results come out, we make sure if you look at the data, it's not going to make sense unless you graph it. We use a pie chart, we use a bar graph. So when you graph everything, you're going to start getting observations. You're going to start getting ideas. But if you only have tables, it's not going to make any sense to you. So yourself, you need to make graphs so you can understand the data better and make better observations and make better discussions. And in the end, you share your experiment not with the people on the Facebook or the people on Dunkin' Donut, you share it with the people on the lab next door, the peer review expert, your colleague, your scientist colleague. So you get qualified expert feedback. Those are the critical evaluation by other experts, not by other people that have nothing to do. Now people are looking for medical advice on the Facebook. People are looking for life advice on the you people that you give $5 to, they read your palm and tell you about your social life. They're not experts, but people go to them. So you always have to go to experts. Yeah, people look in the stars, and yeah, people do that for $5. I don't think so. It should be more. That's why I tell you it doesn't make any sense. Pressure, selection pressure. This is very important. Now, students tell me, oh, professor, I went to the gym, and, let me show you my 30-day bicep transformation. I evolved. Evolution. Evolution takes thousands of years. That is not evolution. Evolution is when you compare the old humans to the Homo sapiens. The cavemen, the ones in Geico, that's evolution. Like we don't look, our brain size is not the same, our skills are not the same, our digits are different. That's evolution. But what you're doing in the gym is a minor hypertrophy. You stop going to the gym, you'll go right back. So this is not evolution. Evolution has to take thousands of years. So what is evolution? Evolution is when you acquire selection traits that will allow you to survive. So you guys now are here. You made it through COVID. You think everybody made it through COVID? No, because they didn't have the successful. Many young people, by the way, died from COVID because they didn't have the selection pressure, the selection traits to allow them. You do. Now, years later, something else they're gonna show up. Are we gonna make it? I hope, but absolutely not all of us. So it's like that. So natural selection is when there are forces that promote the success. There are also social in the society. Some people are able to survive. They can rent a nice apartment, have a nice car, make ends meet. They can able to put food on their tables, and some people are homeless. Why is it that the case? Because in order to be able to survive, whether biologically or socially, you need to have the proper requirements. You see, now you have to have a college education now. This is not the time where like Bill Gates quit school and he did Microsoft and whatever. You can't do this now. Now, if you don't have a college degree, you will never get a respectable job. You will never get a good paying job, and you're never going to be able to connect. You're not going to be able to pay the rent. You're not going to be able, so you're going to become homeless. So that is very similar. You have to acquire, you're not going to have a job. You're gonna turn, some people turn into crime, some people turn into homeless, some people alternate. They do a little bit of both. Yeah, for some it works. Many rappers end up homeless because their rap is not good for too long. Nobody's rap is good forever. But your education is good forever. Your nursing degree, you will never be poor again. You work many hours, you work overtime, you get vacation, you get high pension. That is, you're gonna secure your future. Okay? So that is so adaptations are inherited features of your anatomy and physiology that evolve in response to pressures that enable the organism to succeed. Like being able to better camouflage and hide around trees from predators. Also, there's some fish called the balloon fish. When it sees like the fish that wants to eat it, it blows itself up so big, the predators run away from it, but they don't know it's just jellyfish that is full of air. If they start to eat it, they will burst it, but they don't know that. They think it's so gigantic and big. So that's an example of an adaptation. Okay. Also being arboreal. Arboreal means when you hang on top of the tree. We know we evolved that to survive. The lion doesn't climb the tree well. So, humans used to hide at the top of trees. Then the animals started to develop and adapt the ability to climb trees. So everybody is constantly adapting and coming up with ways to overcome. Prehensile grip. Human beings are the only ones who are able to pick up a rock and throw it, like the baseball with so many miles per hour. No animal can do that. The lion pack, a whole lion pack, 20 of them running towards you, trying to maul you and eat you. If you take one brick and you throw it in their direction, they will run for their lives because they're not ready for that, and nobody nobody does that kind of thing. Okay, but you have to pick up a lot of rocks. If you get tired, you're done. Yeah, but if you can throw the rock at a lion, the lion will run for its life because they don't know what that is. Prehensile grip, being able to hold the pen. Nobody can do that. The monkey cannot do that. No other animal is able to like hold the pen. That's why we developed writing and reading. They cannot hold and pinpoint. This what's that? Chopstick. They can never hold the chopstick. You can do that. That's called the prehensile grip. And to hold the rock, that's something we developed to survive because we used to live with these animals. Sometimes they come to visit us every once in a while. Did you guys see the video on YouTube when the tiger came into the building where the people used to in the neighborhood? Yeah, I think they miss us. Back in the day, we used to all live in the jungle, in the forest, like Tarzan. But now we're beginning to build human societies and move away from them and fight them and throw the rocks at them and protect ourselves from them. And they keep, like I said, they keep visiting us unexpectedly from every once in a while. None of them made it to New York City, but the shark comes to Coney Island every once in a while. It loves being there. Whenever it's in the mood for human leg, they come there. Okay. Bipedalism, being able to stand and walk in 2 feet. because that is very helpful in survival, in our survival, and in our ability to help you in reproduction. You know, there are some people called feral. Anybody heard of feral children? Feral children. Feral children. Feral children, meaning they are children of the forest. You know, people, when they have illegitimate, illicit sexual relations and there's a baby, in some societies of the world, that is not accepted, so they throw the baby away. And they throw the baby away in the forest. Or they are poor, they cannot sustain the baby, throw it away. Or the mom, she is not ready to be a mom. She was ready to have sexual intercourse, but she was not ready to have to be a mother. And when the baby came out, she is heartless, so she threw the baby away. But because the father is not paying child support, many scenarios. But in the end, the poor baby was thrown where? In the forest. What happens to that baby? That baby is now will never be able to walk on 2 feet because it has been living around the animals. Anybody heard of Mowgli? Yeah, Mowgli is a real story. There's many Mowglis around the world, but he made a story to bring attention. Oh, Mowgli, you got to look that up. Mowgli. I grew up watching it. It's not Tarzan. It's similar, but how's Tarzan can walk on 2 feet? Mowgli couldn't walk on 2 feet, did he? Yeah, I think he did.
He met the people. That's how he learned from them.
He met the people. So the thing is, that's the critical issue. It's called the critical age. There's a certain time in your life as a baby. It's either you learn to walk on 2 feet at that time, you'll never again be able to walk. Even if you meet the people, even if you bring a feral child, there's so many millions of them around the world. In Asia, in Africa, when they bring them from the forest to the modern societies and try to make them stand up and walk, they don't walk. They just crawl, just like the animals. It's called the critical age. I think it's from 3 to 4 to 5. That's why the little babies, they see people walking on 2 feet. Now they want to stand up. They want to hold on to the table. Yeah, my little nephew, my table, everything on it is on the floor because he keeps pushing it. So now the babies, they're able to because they see, they observe, they have the sense, they observe people walking, they want to walk too. People are talking, they're talking too. Sometimes adults are having a conversation, the baby wants to be heard too. They want attention too. That's how we learn, that's how we develop. So bipedalism is important for our survival, and it happens in a critical time. If you don't walk in that time, then you'll never be able to walk again, no matter what. It's very strange. Okay. We are here. Now that's evolution. The Homo genius, 2.5 million years ago. Homo erectus, 1.8 million years ago. Homo sapiens are 200,000 years ago. And supposedly in a couple of other 100,000 of years, a new human is going to show. But I think we're the last ones. I think it's too much. Yeah, I think Trump is going to end. The whole world is going to end. I think the whole world is going to end now. But yeah, now we are, if they ask you on the exam, who are we? Are we Homo genius, Homo erectus, and Homo sapien? We are the Homo sapien. We are the last. We are the iPhone, what is it, 17? The last one. Yeah. 18 came out? It's coming out? Okay. Okay. Now, this is the hierarchy of life. We talked about that. Human organization is based on successive levels of hierarchy. Organisms are composed of organ systems. Organ systems are composed of organs. Organs are composed of tissues, and so on and so forth. So we build up the structural hierarchy. But remember, cells are composed of organelles. Organelles composed of molecules. Molecules are composed of atoms. Look at that. You see there, we have atoms, many atoms give you a molecule like carbon with hydrogen, hydrocarbon. Then you have an organic micromolecule, then you have a macromolecule, then many macromolecules give you organelle, many organelle give you a cell, many cells give you tissue, many tissues give you organ, many organs give you organ system, many organ systems give you a baby, and we move on from a baby to baby to organ to population and so on. Okay, we discussed that. What is reductionism and holism? Reductionism, scientists they never agree on anything. So some scientists said the best way to study is reductionism. You take a whole organism and you reduce it, break it apart to smaller pieces. You break down the organism into organ systems, into organs, into tissues, into cell, into organelle, into macromolecules, micromolecules, and then the atoms. Some other scientists said, no, it's not reductionism is the best. It's being holist. Holist is when you go from the little bit, from the small to the top. Both are important. You have to master both. You have to master the reductionism, breaking down the triangle and building up the triangle holism. Good. So reductionism and holism. Okay. The anatomy and physiology we learned is right to about 90% of the world. But does that mean every single human being has the anatomy and physiology we're studying in the book? For example, everybody has 5 digits, 5 fingers. Is every single human being in the world has only 5 fingers, or there's some people with 6? I went to middle school with one. He had 6 fingers. Okay, so that's called the anatomical variation, diversity in the anatomy. That's not physiological variation. You need to know the difference because you'll be asked, is this scenario an example of anatomical variation or physiological variation? So anatomical variation is when there is a variation that is different from the standardized norm. Everybody has 5 fingers, somebody has 6 fingers. That is not physiological variation, that is anatomical variation. So why do we need to study the variation, especially the surgeon? Because this here is a very interesting phenomenon. It's called situs inversus. Situs inversus means that the abdominal structures are switched. So usually, remember I was saying earlier, the right hypochondriac region, you have the liver. The left hypochondriac region, you have the spleen. Some people, it's reversed. The spleen is on the right side, the liver is on the left side. So as a surgeon, you want to do a surgery, you can say, well, I don't know. We only know, we only used to do surgery to people that have a liver on the right side. No, you have to study the anatomical variation. There's also physiological variation. For example, between men and women. You see, men consume 2,800 calories per day. Women, they consume only 2,100, only 100 calories per day. Both are human beings, but our physiology is a little different. We burn a lot more fat than women. Women utilize and save up a lot of fat. Supposedly, men burn out a lot of calories that they need to go work and lift things up and hunting and gathering and moving, and women they stay in the home with the children. That's how the biology was. Now women they have 20,000. The calorie deficit is different, which and also is not only physiological variation between men and women. The age. Children they have their own doctor now, pediatric. Adults have their own doctor now, internal medicine doctor. The very old have their own doctor, a geriatric doctor. For example, a very old patient coming into my office, when I measure their blood pressure, is 165/95. Sweet, no problem. But one of you, 195, 165/95, that's a big problem. So now that's a physiological variation. Why? Because their heart has been pumping for so long Now 195 over or 165 over 95, that's okay. Considering it's like you have a really old car and it's going, considering the mileage, that's okay, that's normal. But for you guys, so you need to understand the physiological variation. Otherwise, you're gonna say this old person has a very high blood pressure. Oh my God, let me give them a blood pressure medication to drop down the blood pressure. You're gonna make a problem for them now. You're gonna misdiagnose them. I almost did that when I was in medical school. Like, oh, his blood pressure is 165. Are you okay? The doctor said, what are you doing? How old is he? Like 75. I don't know. That's why you need somebody to point you. But yeah, this is physiological variation. Now that's our anatomical variation. Normally, your kidneys look like that. Your kidneys are not like 2 years. They're not level. The right, is this right or left? Which is this right or left? This is right. And as you see, it's a little bit depressed. Why? Because on the right hypochondriac region, the kidney lobe, not the kidney. The liver lobe is pressing down on the kidney, bring it a little bit down. Now, does that mean everybody has a kidney like that?
No.
No. Some people have a pelvic kidney. They have a kidney in the normal. They have a kidney in the normal. Okay. They have a kidney in the pelvis and then the kidney in the normal. The people have a horseshoe kidney. Their kidneys are corrected. Is that a disease? Is that no, it's not a disease. That's a variation. I told you. Physiological anatomical variation. It's like when somebody has an extra finger. Is that a disease? No, that's an anatomical variation. If somebody has a pelvic kidney, anatomical variation. If somebody has a horseshoe kidney, anatomical variation. Some people even love to have the anatomical variation. The person with 6 fingers, they said I can play the piano better than anybody else. Right? Playing the piano with 6 fingers. And normal, that's the normal heart. And you see some people have a different, we will talk about this, different branches of the aorta. And you see the brachiocephalic trunk is being divided in different fashions. But in the end, you're getting the oxygen. So I remember one of my students, she had a bicuspid aortic valve. You see, there's only one valve with two doors. This is the mitral valve in the left heart. Is the left atrioventricular valve. That one has only 2 cusps. That student, she had every other cusp, every other valve in your body is tricuspid. Looks like this. Every other valve, bicuspid valve looks like that. Tricuspid valve has 3 doors like this. He's supposed to have an aortic tricuspid valve. She had a aortic bicuspid valve. It's just an anatomical variation. It's not a problem. It's not a problem. Yeah.
But are there differences like in the performance?
No. If there was a difference in the performance, it would be a disease, a pathology. But this is a variation, not an anatomical disease. It's an anatomical variation. Okay, this is a really important slide because it's showing you what are the features of life in order to be called alive. You know, if you ask anybody, what is life? If you go to a mosque, if you go to a synagogue, if you go to a church, we say that life is when God puts soul into you. Life is soul. Life is soul. In science, we don't have soul. So they cannot define life. So they said, let's have characteristics of life. We don't know what life is. We can't define life, but we can define what looks like alive. What it means to be alive. We don't know what is life, but we know what it means to be alive. Number 1, organization. Living things are highly organized. You have organ system and organ and tissue and cells and these macro and macromolecule and subcellular compartments and so on. All living things are made up of cells. You don't have a cell, you're not alive. Number 3, being able to do metabolism, storing anabolism, breaking down catabolism. That's a sign of life. Responsiveness, being able to move, excitability, responding to electric stimuli. We also have homeostasis, maintaining a constant state, internal state, no matter what happens on the external environment. Development, being able to mature, differentiation, proliferation, reproduction, and the evolution. These are the characteristics of being alive. The physiological variation, that's what I was talking about earlier. For a man who's 22 years old, he needs 2,800 calories. Women the same age and her weight is not 154 pounds. She weighs a lot less, 128. And 22 years old male is 154 pounds. When I was 22, I was 254. I was 100 pounds over the reference. Anyways, 128, and they need 2,000 kilocalories. Yeah, because you need 2,800 kilocalories a day. I was having 2,800 kilocalories a meal. That's not good. Because your triangle at the time, I didn't know what I was doing. I was smart. Always you're supposed to have at the bottom a lot of vegetables and a little bit of food. A little bit of food, a lot of vegetables, a little bit of meat, a little bit of food. Oh, I'm losing it. A little bit of carbs. Because you need essential amino acids that your body cannot make. You gotta take them from outside. Did you guys hear about the woman who only ate fruits? And she died? Oh, she died. What are you talking about? She died. I'm sorry. That she looked bad. I was like, she looks dead. And then they said she was dead. But she looked very bad.
But she was starving herself.
She was starving herself. I wish I could do that. I could lose a couple of pounds.
You had to eat it.
Yeah, because she only eats fruits. Who told her to do that?
I don't know.
Yeah. See, you hear something on social media, you change your whole life. And then you die. Homeostasis. Homeostasis. What is you need to know homeostasis? This is really important. This is really, really, really important. What is homeostasis? Homeostasis. Homeo plus stasis. Homeo means the same, right? Homeo means the same. Stasis means constant. Homeostasis means staying constant by staying the same. Staying constant by staying the same. So what does that mean? You see, in your body, you have a U range, EU. You don't want hyper. You don't want hyper. You don't want hypo. You don't want hyper. You don't want hypo. Hyper is when there's an increase. Hyper is when things go above the U range. Hypo is when things drop below the U range. Hyper is when things increase, and hypo when things decrease, and U when things are about even. Now, give me an example. You don't want hypotension. Hypotension means that the blood pressure drop. Hypertension, blood pressure increase. You want eutension. For temperature, you don't want hyperthermia. That means it's too hot now. Hyperthermia is too hot. Hypothermia is too cold. You want euthermia. Calcium. You don't want hypercalcemia. You don't want hypocalcemia. You want eucalcemia. Always you. You don't want hyper anything. Hyper is bad. It's not like the more the better. Hyper anything is bad. Hypo anything is bad. So your body is equipped with built-in systems that whenever we deviate from the healthy U range down, we can bring things back up again. That's homeostasis. So homeostasis is to maintain a constant internal homeostatic U range, no matter what happens on the outside. For example, right now, if they measure your temperature, it's 36.6 degrees Celsius, 37 degrees Celsius. If you go out in snow, you're gonna shiver, but your temperature is still gonna be 36, it's gonna be 37. Let's say the euthermia is 37 degrees Celsius. Euthermia is 37 degrees Celsius. Clear? If you're too cold, it's gonna drop down, minus. It's gonna become 26 degrees Celsius. Now that's cold. So what does your body do to bring it up? Shivering. You're gonna do shivering thermogenesis. Shivering thermogenesis. Shivering thermogenesis. And then you're gonna warm up. What about in the summer when it gets really hot, 38 degrees Celsius? Your temperature now has become hyperthermia. How do you bring it down? You're sweating. When you're sweating, that's gonna cool you and bring you down. Well, whether you're sweating or shivering, the temperature is gonna stay the same at the U range, 37 degrees Celsius. That's what homeostasis means. It means no matter what's happening on the outside, your body is able to maintain an internal constant U range, homeostatic range. Okay, so now if we look into another thing, your shivering thermogenesis is another example of how we respond to cold, but also your blood vessels. Ever had your car overheat? The car is so hot. Why do they tell you never open the radiator when the car is so hot? Because the water is gonna flow out and it's gonna burn you. Why not now when you open the radiator and the car is on? Why doesn't the water run out at you? Why is it only when it's too hot the water runs at you? Because the engine is so hot. The water job is to be around the engine. You remember the balloon earlier full of water? So the water is gonna suck all the hot energy from the engine. Then it's gonna go up to the car and it's gonna rotate. The valves are gonna open and the hot water is gonna be rotating on the external tubes. Why? So the heat can flow out from the tube to the air. Same thing your body this way. So when you're hot and you don't only sweat, the blood vessels around your skin are gonna open wide to accommodate a lot more hot blood, and the blood is gonna flow out. The blood is gonna flow out from the skin to the air, and you're gonna cool. This is how you cool down. When you're cold now, you're cold, so you have a little bit of heat in your viscera. So all the blood vessels on the outside, are they gonna be wide or are they gonna tighten up? They're gonna tighten up because if they are wide, the little bit of heat you have is gonna escape. So we utilize these tubes near the skin to exchange heat with the outside environment. So now there's two types of mechanisms. There is negative feedback. Negative feedback. Negative feedback now, what does it mean? Negative feedback means that number one, you have a sensor. You have a sensor or a detector, a sensor, detector, receptor, all the same. Receptor, the receptor and the detector is gonna notice there is either some increase, hyper, or some decrease, hypo. Some increase, hyper, or some decrease, hypo. Are we clear? The sensor is going to detect that. How did your body know you're too cold? Let me make you shiver. How did it know it's too hot? Let me make you sweat. Because of the sensor. We have different type of receptors. Thermoreceptor for heat. Chemoreceptor for touch. Mechanoreceptor is for touch. Nociceptor for pain. Proprioceptor for balance. Osmoreceptor for osmolarity. Different types of sensor because we sense different things. So the receptor is going to send an input signal to the control center, the processing center, the integration center. Many times it's the brain, but sometimes it's not the brain. And then the brain is going to generate out an output. And the output is going to go to the effector. And the effector is going to restore the homeostasis. For example, thermoreceptors will detect you're too hot. They're going to send information to the brain. The brain is going to send information to the sweat gland, the effector, to do the effect of cooling. You know, you see the crime, you call the police. You don't call the police. You call 911 center. You are the receptor. You are the sensor. You are the detector. You detected, you receive that there's an information problem. You call the 911 control processing center. Then they are the one who tell the police to go. They have the effectors to bring the effect. Firefighter, they send the effector, the firefighter. So the effector is the one who does the effect of homeostasis. Now, let's look at, so this is negative feedback. So why do we call it negative feedback? Negative feedback because you were too cold, temperature dropped. Okay. When temperature dropped, you shivered. When temperature dropped, you shiver and temperature increased. So we call it negative feedback. Negative because you resolve with the opposite. Negative doesn't mean minus. Or when the temperature increases, you cool with the sweat. That's negative feedback. Negative feedback is when the input and the output are opposite. You were so hot, now you're so cool. You were so cold, now you're warm. That's called negative feedback. So medication is all about negative feedback. Imagine your blood pressure, your blood sugar is so high. You go to the emergency room, they give you insulin to bring it down. That's negative feedback. But if you go to the emergency room and by mistake they give you glucagon, so now you have too much blood pressure, now you have even more blood pressure, even more blood sugar is high, now you have a coma. That's an example of positive feedback. Positive feedback is when you make things that are high, higher. Or when you make things that are low, lower. You have no sugar in your body. You go to the emergency room so they can give you IV with glucose, or they can give you glucagon to increase sugar. By mistake, they give you insulin. So you had no sugar in your body. Now you even have no more. So that's another coma. That's an example of positive feedback. So they need to do negative feedback. You have no sugar, give you something to increase sugar. You have too much sugar, you give something to decrease sugar. Yeah.
For example, if there's labor contractions, then.
We're getting to that. That's positive feedback. We're getting to that. So positive feedback is a vicious amplifying cycle. That's what I'm saying, that if you don't treat medication with positive feedback, you treat it with negative feedback. Now, if you look at what your classmate said, now, if you look at what your classmate is saying, that we, during labor contraction, the baby push against the cervix. So the receptor in the cervix will send to the brain that the baby is pushing. So the brain will send to the uterus, the effector, push out. So the baby push and the uterus push out. Baby pushes, uterus pushes out until the baby comes out. That's positive feedback. The more the baby push, the more the baby comes out. Breast milk. When the baby is suckling the breast milk, irritating the nipple, nerve ending. So the more the baby irritates the nipple, the more milk come out. That's positive feedback. So we use positive feedback for the birth and for the suckling the breast milk. And what else? What about platelets? The Band-Aid. When you cut yourself, there is a laceration, when there is a bruise, a contusion, the blood is starting to leak out, then the platelets will come, like Band-Aid. One platelet will stick, then the second platelet, then the third, then the fourth, then 10 more, then 15 more. So that is an example of positive feedback. So we use positive feedback for platelets, for red blood cells, for birth, labor, and also for milk, breast milk. Okay, there we go. If too warm, the skin blood vessels dilate. That's vasodilation, to accommodate a lot of more hot blood so we can shunt away all of the heat. So that is showing you now the negative feedback cycle. So you see here, the room temperature falls to 19 degrees Celsius. What is that? Hyper or hypothermia? It fell. The room temperature falls. So what is that? Hyper or hypo? That's hypothermia. Then who detected that? The thermostat detected it. So like a thermoreceptor. Then it processed that, listen, let's activate the furnace. What is the furnace now? Effector. Excellent, because the furnace is the one who did the heat. So who made us warm? Because the temperature dropped, we were cold. Who made us warm? The furnace. So the furnace is the effector, the one who makes the effect. So now the room temperature rises back, and then we shut off the furnace. Now everything is okay. Are we clear? So that shows you we're supposed to be at this set point in the middle, U, 37 degrees Celsius, euthermia. If temperature goes up to 37.5, oh boy, we're going to vasodilate. Blood vessels are going to vasodilate, and you're going to be sweating, and then all the heat is going to go down. If you look now, if you're cold, if temperature drop from 37 to 36.5, it drops. When the temperature drops, what happens? You're going to shiver, and that is going to bring the temperature back to the set point. Are we clear? Another example. Okay, we're going to talk about the baroreceptor reflex, but look at this. The reflex has a receptor. We said that. Receptor, detector, sensor, integrating center, that is control center, and effector. This is where the cell or the organ carries out the final corrective action. Are we clear? This is what happens. You see, when you wake up in the morning, don't get up and start walking. Why not? Because look at the balance. The balance is, there's an imbalance because when you were sleeping, all the blood is pooling down to your neck. Your brain doesn't have a lot of blood. And where are the centers for balance? They're in your brain. So when you get up, you have to wait. Why you have to wait? You have to give time for the receptors to detect that, hey, blood is pooling down to the neck. We need to increase blood pressure and increase blood pumping to the brain. So there are receptors close to the heart that sense that the heart rate is low because you were sleeping. So the brain is gonna, these receptors are called baroreceptors. They're gonna go to the heart and tell the heart, they're gonna go to the brain, and the brain is gonna feed back to the heart, tell the heart, pump faster. So the heart is gonna pump faster and faster so that the blood is gonna now go back to the brain, then you're gonna balance. So when you get up from the bed, don't start walking. Sit up for a little while. Sit up. Pray for a little while, then get up. See, thank you, God, for bringing me back to life. Do that kind of stuff, and then you will see that the blood is going to start to flow to the brain. Then you can walk. But if you just do like me, one time I had to teach a course 8 a.m. in a very far school in Long Island. So I had to leave around, like, I had to wake up 5 a.m. so I can leave by 6 a.m. and drive for 2 hours. So, you know, I'm sleeping, and then I woke up. I was like, it probably 8 a.m. already. So I got up and I started walking. I tripped. I turned on the light. It was 3 a.m. But I tripped. Why? Because I didn't have enough time so that my brain can. Hey, this happened today too. Like, you told them don't sleep through class. You better not sleep through class. And I woke up. It was 5 a.m. Like, I was like, thank God. It happened to me one time. I told the class, don't you sleep through my class. And then I slept through the class. Yeah, that was bad. I never did it again though. Yeah, they were nasty. Okay, positive feedback, self-amplifying. So, self-amplifying is not good for treatment, but it's good for other things. It's like a junkyard. Some people junk, some people need it. Right? Old equipment in your car, you don't need to use it. Somebody will pay money for that. So the positive feedback is a self-amplifying cycle. We said an example of that is childbirth, blood clotting. Another example is the runaway fever. So the fever keeps on. That's why for fever, you need to put a cold pad, not very cold, just to absorb the heat from the brain to the pad. That's the mom. You see, the baby is the one who is pushing the cervix, and the receptors are here, sending down. These are mechanoreceptors sending down stimulation to the brain, telling the brain that you need to send information to push. So they secrete the hormone oxytocin, and oxytocin is going to push through the cervix. So after you do the homework, read the chapter, so when we come to lecture, you can understand better. But if you just show up to lecture, you have no idea what's going on, you're not really going to get the most out of the lecture. You're going to be confused. Yeah. Okay. Just chapter 1. So gradient are different disparities. So a gradient is a difference in chemical concentration. There's a downhill gradient from high to low. There's an uphill gradient from low to high. And this is the high blood pressure. So from closer to the heart, that's high blood pressure. Then you go to where there is low. Then you go from your next to your heart where there's high blood pressure to your toes where there's low blood pressure next to your toes. So the blood pressure goes from an area of high pressure to low pressure. Look at here, glucose flows from where there's a lot of green glucose to where there is a little bit of glucose. That's a chemical gradient. That's a pressure gradient. This is positive and negative charge. Those are electrochemical. So you have like sodium and chloride. Sodium is positive, chloride is negative. So they are both chemicals, but they are charged chemicals. That's why we call it electrochemical. Heat. That's what I was saying earlier. These are the blood vessels carrying blood, and the heat is flowing from where hot blood to the cold. Oh, now I know what's happening. Their wires are weak. Okay, these are the major themes. There is a unity and interdependence between form and function. And this is the evolution and homeostasis, the balance, and gray matter and energy tend to flow down concentration gradient. So radiography, you see, these are radio-opaque substances. They can be injected or swallowed to fill the hollow structures. And there is digital subtraction and geography. And that shows you if there's any blockage of the blood vessel. That shows you the X-ray, that's for diagnostic. Computer tomography, that takes place through the transverse section plane. And this is the MRI. Sonography is the second oldest and second most widely used to diagnose the development of fetus. Any questions? Are there any questions? No questions.